Alright, so we've got another example here where we're going to find all the answers to these questions based on a given compound. Our first mission is to find out what chiral centers we have in the compound, and any carbon that has 4 different groups attached to it is going to be a chiral center. That's not chiral, that's not chiral, and that's not chiral because they don't have 4 different groups. This carbon is chiral and this carbon is chiral because they do have 4 different groups attached to them. That's not chiral and that's not chiral. Alright, so we figured out our chiral centers. Our next thing is to find out how many stereoisomers are possible. We know what the rule is here, and that is if there are n stereocenters, we're going to have n 2 to the n stereoisomers. So that would be 2 to the n equals 2 squared equals 4. In this case, it would be RR, SS, SR, and RS. Those would be the 4 possible stereoisomers for 2 stereocenters. So we're actually going to figure out what these are really assigned. Now the first thing we want to do is look at each chiral center and get the lowest priority group into the back. Now as I've talked about before, the back position is the top and the bottom of the structure. Remember, these are Fisher projections and these are actually both pointing backwards. Alright, so I'm going to move the lowest priority group into the back, and in each instance here the lowest priority group is going to be a hydrogen. So the hydrogens need to be at the top and the bottom respectively of this structure. Alright, now when I'm doing this, I leave the backbone alone and I just rotate the groups around so that I can get the lowest priority group into the back. Now when I rotate these around, I'm not changing the stereochemistry of either of these chiral carbons. All I'm doing is rotating the molecule. Alright, so when I do that, I'm going to put the hydrogen up here. The CH2, CH2, CH3 moves on to this one. So you see the H goes up here, this group goes down here, the NO2 moves over to the other side. And notice I keep the N connected to the C, and that's what I've done over here as well. Now down on the bottom one, we're going to get the hydrogen moving down here. The F will move over here, and the CH2, CH3 will move over here. Now, if you look at what's connected to the C here, it's actually the CH2 group, and what I've done by rotating this is moving the entire group over here, but it still remains, the C will be still connected to the CH2. So it's going to be incorrect for me to make this CH2 and make this CH3. I want to keep the connectivity the same as this thing rotates around. Alright, so now we've got the lowest priority groups in the back in each case. I'm going to redraw this, and I'm going to handle the chiral centers separately. So this would be H, CH2, CH2, CH3. Alright, so we're going to look at the top chiral center first, and I'm going to assign priorities to the top chiral center. Alright, top chiral center. Alright, so first of all we look at what's connected to the C that we're talking about. And that's an N, a C, and a C, and an H. Well, the H is already the lowest priority group. We're not going to worry about that. So it's going to be between the N, the C, and the C. Out of the N, the C, and the C, the N takes top priority. That'll be group 1. So now we've got a C and a C. The question we've got to ask about each of these C's now is, what is the heaviest atom attached to each of these C's? Well, we move on. The next atom attached to this C is a C. The heaviest atom attached to this C is an F. That means this group here be the winner, and this group will get number 3. So these are the 3 groups, or 4 groups I should say, attached to the top chiral center. And this will be 1, 2, and 3. And since this is going in a counterclockwise direction, this is going to end up being S. So the top chiral center is going to be S. Now we're going to focus on the bottom chiral center, that's this one down here. So we look at what's attached to it, and what we see attached is an H, a C, and an F. Now out of the H, the C, and the F, we know the H is lowest priority. The F will take number 1 because it's heavier than the C. Next we look at the C's and we move on to see the heaviest atom connected to each atom. The heaviest atom connected to this C is a C. The heaviest atom connected to this C is an N. So this group will be the winner. So this will be number 2 and this group will be number 3. And those are the 4 groups connected to the bottom chiral center. Alright, so now we look at the direction of flow from 1, 2, and 3, and we see it again, it goes in a counterclockwise direction, so it's going to be S as well. So the top is S and the bottom is S as well. So we next need to figure out what the name of this compound is going to be, and I'm going to show that over here. I'll take the original structure so that I can get the name of it, although I could have just used one of these structures as well. Now when I'm figuring out what the line structure looks like so I can name it, what I want to do is pretty much ignore any of the hydrogens attached to any of these carbon atoms and then come up with what I believe the structure is going to be. So we're going to get rid of that, and what the structure is going to look like is this. We'll have that would be the C, and the C. We'll connect that down here. That's this C here, and that's this C here. And then we'll have an NO2, and we'll have the F down here, and then we'll have the CH2 and the CH3. So now adjusting that line structure, we'll have 1, 2, 3, 4, 5, 6, 7 carbons in a row. 1, 2, 3, 4, 5, 6, 7. And these 3 C's will be these 3 here. Then we've got the C with the NO2, and then we've got the C with the F, and then we've got the CH2 and the CH3. So that's those carbons right there. Then you've got the C with the F, the C with the NO2, and then the 3 carbons in a row at the end. So that is what the line structure would look like for this compound. Now we've already established that that's going to be S and that's going to be S, and we figured that out based on these assignments over here. Now remember that by rotating this hydrogen into the back, I did not change the stereochemistry of this original compound. Rotating only just puts the lowest priority group in the back. It does nothing to change the stereochemistry of either of the top or the bottom center. Now that I've got a line structure, I can figure out a name. And the numbering for this would go from this end. It'd be 1, 2, 3, 4, 5, 6, and 7. So we know it's going to be a heptane. going to go ahead and delete some of this so I have a bit more room to work. And the name for this then would be 3s, 4s, to put the stereochemistry in, and then it would be 3 fluoro, 4 nitro, and this has to be in alphabetical order, F, N, and then this is all still part of the same word, heptane. Alright, so that would be the name of that structure. Okay, now the next thing we want to do is get an enantiomer and a diastereomer of this compound, and we're also going to name those as well. So the initial compound is going to be 3s, 4s. Now we're going to figure out what the enantiomer looks like. Alright, so I'll erase this down here. I will redraw the compound. Now when I redraw this, I can either use the initial compound or I can use one of these compounds here where I've put the lowest priority group in the back. I think I'll just use the ones where I've got the lowest priority group in the back, although I don't have to. Now to get an enantiomer, the easiest way is just to get a mirror image of this compound. And when I do that, this will be S and S. And when I do that, here's your mirror right here. The NO2 will be over here. The CH2, CH2, CH3 will be here. The F will be here. The CH2, CH3 will be over here. And the H will be down here, and the H will be up here. Now since I'm getting the mirror image, I automatically know, I don't even have to check this, I automatically know what's going to happen is the S will switch to an R, and this S will switch to an R. So whatever stereochemistries you have over here will reverse on this side, and that will be the enantiomer. The name of this enantiomer then would be, well, since the numbering is going to be the same, it's going to be 3 fluoro 4 nitro. Remember, this is 1, 2, 3, 4, as it was on the initial structure. And this would end up being 3R, 4R dash, and then this entire name down here. Alright, so that would be the name of the enantiomer. Now what I want to get is a diastereomer. Now to get a diastereomer, what I can do is I can base it either on the enantiomer or the initial compound. It doesn't matter which. The enantiomer, the diastereomer of the enantiomer is still a diastereomer of the original compound as well. Now to get a diastereomer, what I do is I leave one of the stereocenters the same and I switch the other one. So I'm going to draw the diastereomer down here, and what I'm going to do is I'm going to leave the top one the same and switch the bottom. Although I can also get a diastereomer by leaving the bottom the same and switching the top. But I'm just going to go ahead and leave the top the same. So let's use the NO2 here, and it will still be S, so that's not changing. Now to change the stereochemistry of the bottom one, all I have to do is switch two groups. So if I switch the F and the CH2CH3, that will be enough to change it so that the stereochemistry switches. Alright, so there you go. That's going to go from an S to an R. Now if I left this one the same and switched the top, then this one, lower one, would have been S and that would have been R, and that would have been a diastereomer as well. Interestingly, it would have been the enantiomer of this diastereomer. The definition of an enantiomer is a compound that has all its stereocenters switched. A diastereomer has just some of them switched, and that's what's happened here. We've left one the same and switched the other one. So this is the diastereomer down here. And the name of it would be, well, that's the 1, 2, and that's the 3 and the 4, would be 3R, 4S, and then the rest of that name down there. And that would be your diastereomer. Now the last part of the question asks, are there any meso stereoisomers here? And I would look at all of these and I don't see any that have a mirror plane. So the answer to that question is no. None of them have an internal mirror plane, so none of them are meso. Alright, just let me make one other thing clear, and that is when you've got the line structure, which I'll redraw down here, so that was the line structure we had. It's important to know how to number this and then how to number the original structure. And I do this by looking at where the fluorine is, and I see that's on the 3 carbon, so I would automatically number that 3 and number that 4, and then I can number the rest of the molecule. So that's an important point to keep in mind when you're naming the diastereomer and the enantiomer, making sure that you took the original numbers off the line structure and put them on correctly onto the initial compound.